Good afternoon, friends. This is our next lecture for digital communication. In that, today we have to cover the topic maximum likelihood decoding. Okay, likelihood decoding. In this method, before starting, we take the basic concept of that. What is maximum likelihood decoding? What happened in that? We are going to study here. Maximum covered the techniques of hard and soft decision decoding. It's time to illustrate the most important concept of maximum likelihood decoding. Then maximum likelihood decoding. Consider a set of possible code words, valid code words said, okay, generated by encoder in the transmitter side. We pick one code word out of this set, call it, okay, and transmit it via a binary symmetric channel BSC, which we have studied earlier in previous lectures, with probability of error. To know what is a BCS, okay, at the receiver side we receive the distortion version of, call this numerous code word y, okay. Maximum likelihood decoding, choose one code word from the list of all possible code words which maximizes the following probability: p is equals to y sent bit x received bit, okay. Meaning of that, the receive computes, okay, and close this a code word which gives the maximum probability in practice, okay. We don't know at the receiver, but we know. So how to compute the probability? Maximum likelihood estimation, MELE, come to our rescue for a detailed explanation on MLE, okay. The aim of maximum likelihood estimation is to find the parameter value that make the observed data most likely, okay. Understanding the difference between prediction and estimation is important in this point. Estimation differs from prediction in the following way. In estimation problem, likelihood of the parameter is estimate based on given data observation vectors. In prediction problem, probability is used as a measure to predict the outcome from known parameters to a model. Okay, example for prediction and estimation. Probability of getting ahead in a single toss of the fair coin is, okay, 1. The coin is tossed 100 times in a row. Prediction helps in predicting the outcomes head or tail of the toss based on the probability. Second is the coin is tossed 100 times and the data head or tail information is recorded, assuming the event follow binomial distribution model. Estimation help in determining the probability of the event. The actual probability may or may not be. Maximum likelihood estimation estimates the conditional probability based on the observed data, received data, and assumed model, okay. Example of maximum likelihood decoding. Let y is equals to 1 1 0 0 1 0 0 1 and x is equals to 1 0 0 1 1 0 0 1. Assume binomial distortion model for the event with probability of error 0.1, okay. That is, the reliability of the BCS is 1 minus p, that is equals to 0.9. The Hamming distance between the code word is 2. For binomial model, probability p is equals to y received s to x send, then 1 minus p raised to n minus d into p raised to d, where d is the Hamming distance between the receive and send code word. n is equals to number of bits send. Okay, p is the error probability of BCH, and 1 minus p is equals to reliability of DSC. Substituting d is equals to 2, n is equals to 8, and p is equals to 0.1, then we will get 0.005314. Okay, got how to calculate? Okay, the note is for here for you. Here Hamming distance is used to compute the probability, so the decoding can be called as maximum distance decoding, which minimizes the Hamming distance, or maximum the likelihood decoding. Including distance may also be used to compute the conditional probability. As mentioned earlier, in practice y is not known at the receiver. Let's see how to estimate parity. Y receive as to x send, then y is unknown based on the binomial model. Since the receiver is unaware of the particular y corresponding to the receiver computes p y received as to x sent for each code word in y. The y which gives the maximum probability is concluded as the code word that was sent. Okay, now we will going to study this topic in slide base in detail. See here, this is the first slide for maximum likelihood ML decoding. What happened here? ECC code is there, channel in between the ECC encoder and decoder. Clear? What happened here? U is there, here V is there, here V plus N is added. Okay, U dash V dash. Decoder must determine V dash to minimize P E by R is equals to P. V dash is not equals to V as to R. Okay, the probability of error is P of E is equals to summation of P E as to R into P of R. P of is independent of decoding. Its optimum decoding must be minimize P. V dash is not equals to V as to R for all R. Okay, maximum P V dash is equals to V as to R for all R. Choose V dash as a code word V that minimizes the P V as to R is equals to P V as to V R as to V P of V upon P of R. If P of V is the same for all V, that maximizes P of R as to V. ML decoding. Memoryless channel is there. ML decoder maximizes the P of R as to V is equals to pi P of RJ Vj. Alternatively, choose V to minimize the log of PRV log summation of log of PR3Vj. The ML decoder is optimal if and only if all V are equally probable as input vectors. Otherwise, P of RV must be weighted by the code word probabilities PV. ML decoding on the BSC. BSC is a PRGV. 1 minus P if RGV is equals to Vj and P otherwise. Log P of RV, summation of log of P RGVj. Hamming distance, let R and V is the difference in the RV position. Clear? Observe slide carefully what I am saying. Here we recalling the binary BSC technique. Here is the channel capacity Shannon's, right? 1948 it is invented, okay? Every channel has a capacity C determined by the noise and the input power and bandwidth constants. EBR and ECR are positive functions of R. For R is less than C, okay, there exists a block code of length n such that with ML decoding P of E is less than or equal to 2 raised to minus n EBR. Similar for convolutional codes, PE is less than or equal to 2. PE is less than or equal to 2 raised to minus m plus 1 NECR. In fact, the average code performed like this. Non-constructive proof using random coding is there, but ML decoding for long random codes is infeasible. Performance measures. Trade-off main parameters. Code rate is there, error probability is there, word error rate, right? Bit error rate for a given channel and channel quality. Decoding complexity is there. Performance is often displayed as a per of an error rate as a function of channel quality. Error rate curve is there. See here what happened. Here is signal to noise ratio and here is the ER is there. Blue line shows the channel limit. Dotted red line shows the coding threshold. Solid red line shows the coding gain. Uncoded and coding means difference is there. Got it? EB is equals to ES upon R. Here is the asymptotic gain, coding gain. What is here? Asymptotic coding gain is there. Coded and uncoded and coded. Clear? Here is asymptotic coding gain. P uncoded is nearly equals to 1 by 2 into EB by NO. For high signal to noise ratio, BPSK modulation and AWGN channel with soft decision decoding we used. P decoded is equals to SD K decode E D minimum REB upon N0. Asymptotic coding gain is there, which is calculated by using the formula EB upon NO uncoded upon EB upon NO coded is equals to RD minimum. Clear? Or log 10 log RD minimum for HD coding, log 10 log RD minimum by 2. Thus, HD gives 10 log 2 10 is equals to 3 dB better ACG than HD. Here the performance close to the Shannon limit. See, blue lines shows the limit, Shannon limit. Green line shows the turbo code or LDPC code. Okay, red line shows the classic code and black line shows the uncoded. Clear? Coded modulation is there. See this graph carefully, then next graph it will get. coded modulation is there. Encoding plus modulation need a distance preserving modulation mapping that preserve distance between different code words. Thus, we can view coded also in a modulation domain. Combined coding and modulation design code specially to increase distance, exploit that in a large signal constellation. Some points are further apart. No bandwidth expansion with coding, but the constellation is expanded compared to the uncoded modulation. Coded modulation for some scheme work on a single constellation by LN code. Some input bits by an LCC. Let the output be determined a subconstellation. Let the remaining input be determined according to the subconstellation. TCM is the coded modulation based on the convolutional ECC. PCM is the coded modulation based on the block ECC. Also coded modulation with turbo and LDPC codes are there. Here, this is trellis of linear block code which we have yesterday trellis diagram, a representation that facilitates soft decision decoding. We call a linear block code in the raw space of a generator matrix. Example is 000, 011, 101, 110. There is one sender and one receiver is there. Here EEEOO is there. Okay. This is a directed graph, a set of depth or time instance, order usually from 0 to n. At each time instance, a set of nodes, vertices representing the code state at the time instance. Usually in an ordinary block code are initiated state S0 at time 0 and one final state S1 at the time n. Edges can go from a state at time I to a state at time I plus 1. Each edge is labeled by one or more symbols from the code alphabet. Usually binary is there. A sequence of edge labels obtained by transposing the trellis from S0 to SC is the code word. Linear trellis is where necessary but not sufficient conditions for the corresponding code to the linear. There exists an output function OI is equals to F1 S11 where F1 S1I is not equals to F1 SI dash for I is 1 is not equals to I dash. O is the output block from time I to time I. Okay, I1 is the time block from T1 Ti to time plus 1. S is the same state at time I. There exists a state transaction function SR Si1 plus 1 is equals to Gi S1n. More properties of linear trellises the trellis of a linear code, the set of states summation I at the time I is called the state space. The trellis is time invariant if a finite period initial delay V summation of an output function and F and a state transition function G. Template space state space is summation such that I summation of I summation for 0 less than or equal to I greater than V and summation I is equals to summation for I is greater than or equal to V is there. For Fi is equals to F and Gi is equals to G for all I summation of T. Bit level trellis of linear block. NK linear block code C bit level trellis N plus 1 time instant and n release section. One initial state has 0 at time 0 and one final state has 1 at time n. For each time I is greater than 0, there is a fixed number incoming I of incoming branches. For all I, incoming I is 1 or 2. Two branches going to the same state have different labels. For each time I is greater less than n, there is a fixed number outgoing branches. For all I, outgoing I is the 1 or 2. Two branches coming from the same state having different labels. Each code word corresponding to a distinct path from S0 to SF. Right? Bit level release of linear block code. The number of summation I is sometimes called the state space complexity at time instant I. For a linear code, we will show that summation for all I is the power of 2. Thus, we can define the state space dimension. Pi is equals to log 2 of summation I. See this and observe carefully. The sequence P0 is equals to 0, P1, Pi, Pn is equals to 0. The sequence P1 Pi is called the state space dimension profile and determining the complexity of an soft decision decoder for the code generation of matrix duo form. Observe this what happened here. See, here is the trellis diagram, okay, for binary. A convolutional encoder in a finite state machine. An encoder with a n binary cells will have two states, right? Imagine that the encoder shown on the image 1 above has 1 in the left memory cell M0 and 0. In the right one n-1. M1 is not really a memory cell because it represents the current value. We will designate state such a state as 10 according to an input bit. The encoder at the next turn can convert either to the 0-1 state or the 11 state. One can see that not all transactions are possible. For example, a decoder cannot convert from 10 state to 00 or even to the 10 state. All possible transactions shown below. See here for 0001, 10 and 11. All the possible transactions is here. A trail diagram for the encoder or image 1. A path shown through the trellis is shown as a red line. The solid line indicates the transaction where input is 0 and the dashed line shows when input is 1. Observe the diagram. How many paths are there? What are the different? Different possible transactions. Observe carefully. When input is 0, which are the different transactions? When input is 1, what are the different transactions? Clear? And red line shows the path, okay, for 3 days. An actual coded sequence can be represented as a path on this graph. One valid path is shown in red as an example. Okay, this diagram gives as an idea about the decoding. If the received sequence does not fit this graph, then it receives with error and must choose the nearest correct fitting the graph sequence, and real decoding until the exploit the data. Okay, predistance and error distribution is there in this graph. The vertical bit error rates curve of encoded QPSK, recursive and non-recursive subdivision additive with Gaussian noise channel. Curve are small distinguished due to approximately the same free distance and weights. See here the free distance d in the minimum Hamilton distance between the different encoded sequence. The correcting capability of a conventional code is the number of errors that can be controlled by the code. It can be calculated as t is equals to d minus 2 by 2. Okay, since the convolutional code doesn't use blocks processing, instead a continuous by-stream, the value of t applies to a quantity of error located relatively near to each other. That is, multiple groups of t errors can usually be fixed when they are relatively far apart, right? Free distance can be interpreted as a minimum length of erroneous. Okay, burst at the output of the conventional decoder. The fact that error appear as a burst should be accounted for when design of design a concatenated code with the inner convolutional code. A popular solution for this problem is to interleave data before convolutional encoding so that the outer block code can correct most of the errors. Okay, decoding convolutional code. Example for decoding the convolutional code: bit error ratio curve of convolution with different options of different modulations, LLR and all. Longer constant length code are more practically decoded with any of the several sequential decoding algorithms, of which the fan algorithm is the best known. Unlike interval decoding, sequential decoding is not maximum likelihood, but its complexity increases only slightly with constant length. Allow the use of the strong, long, constant length code. Such codes were used in the Pioneer program of early 1970s to Jupiter and Saturn. but give way of shorter, Viterbi decode codes usually concurrented with large rate Solomon error detection correction code that staple the overall bit error rate curve and produce extremely low residential undetected error rate. Both Viterbi and sequential coding algorithm return hard decision, the bit that form the most likely code. An approximate confidence measure can be added to each bit by use of the soft output Viterbi algorithm. CEO. Observe this diagram and graph. Then I will discuss further. Here is the uh, bit error curve of encoded QPSK soft decision, additive wide Gaussian noise channel, longer constant length produce more powerful codes, but the complexity of the Viterbi algorithm increases exponentially. Okay, with constant length limiting these more powerful codes to deep space mission where the extra performance is easily worth the increased decoder complexity. In fact, predefined convolution code structures obtained during scientific researches are used in the industry. This relates to the possibility or select especially popular Viterbi decoded convolution code used at last since the Viterbi program has a constant length k of 7 and the rate r of 1 by 2. Okay, here is the rate of 1 by 6. This code performs about 2 dB better than the simpler code at a cost of 556 into 2 in decoding complexity. Okay. Convolution code with 1 by 2 and 3 by 4 code rate and constant length 7 soft decision for QAM, QPSK and OQPSK. Yeah. Convolutional code with any code rate can be designed based on polynomial selection. However, in practice, a puncturing procedure is often used to achieve the required code rate. Puncturing is a technique used to make a M by N rate code from a basic low rate code. It is achieved by deleting of some bits in the encoder output. Bits are deleted according to the puncturing matrix. The following puncturing matrices are the most frequently used. There is a code rate puncturing matrix. Three distance is there. For NASA standard, key is equals to 7, convolutional code is there. For example, if we want to make a code with rate 2 by 3 using the approximate matrix from the above table, we should take the basic encoder output and transmit every first bit from the first branch and every bit from the second one. The specific order of transaction is defined by the respective communication standard. Okay, punctured convolution code are widely used in the satellite communication, for example, in interstellar system and digital video broadcasting. Punctuated convolution code are also called perforated. Okay, this is the diagram for turbo code. Turbo code is placed in the convolutional code. A turbo code with component code 1315 turbo codes get their names because the decoder uses feedback like a turbo engine. Permutation means the same as the interleaving C1 and C2 are resolved convolution code. Recursive and non-recursive convolution code are not so much different in BER performance. However, recursive type of is implemented in turbo convolution code due to better interleaving properties. This is enough for today. In next lecture we will continue.